So in a normal deck of cards, what's the probability of drawing a jack or higher? So a quick diversion over here to decks of cards. These come up sometimes in these probability calculations. So I know that not everybody has the same familiarity with these. So let's just discuss really quickly what a deck of cards is. A deck of cards consists of 52 unique cards. And each card has two characteristics. It has a suit, hearts, diamonds, spades, or clubs. Hearts and diamonds are considered red cards. Spades and clubs are considered black cards. It also has a value. And these values are the numbers 2 through 10. So 2, 3, 4, 5, 6, 7, 8, 9, 10. The face cards, Jack, Queen, and King. And then the ace. In some circumstances, ace is counted as a 1. But most of the time in things like poker and so on, the more familiar games, ace is often counted as being a high card. So I've listed these in increasing value. So we consider an 8 to be a higher value than a 2, of course, but we consider, say, a jack to be a higher value than any of the number cards 2 through 10. Queen's better than jack, king is better than queen, and quite often ace is the kind of highest value card. Again, it depends maybe on the game you're playing or on the particular house rules of that game or something, but for our purposes, we'll consider ace to be a high card. So if you want to see what the cards look like, you can, of course, Google deck of cards or something like that. Decks of cards also maybe sometimes have jokers. We're not including jokers in the kind of standard deck of cards. So each card has these two characteristics, and each one is unique. So we have hearts, diamonds, spades, and clubs for the suit, and we have 2 through 10. Jack, queen, king, and ace. Running out of room here at the bottom for the values. So we see, for instance, we have a 2 of hearts. We have a 3 of spades, and so on. There's exactly one of each of these different value suit combinations. We have 13 rows, 4 columns. 13 times 4 gives me 52. Okay, so now that that's out of the way, as an aside, for things like decks of cards, for those kind of problems, they won't be on the exams. You might see them on the homework, but you can, either refer back to this or, Google decks of cards or something if it's unclear. If you're unclear exactly what the different suits or values or something are. But they won't be on something like an exam. Okay, so what's the probability of drawing a jack or higher? There are 52 cards, all equally likely to be drawn. And the cards that are in the event are any of these 4 values, jack, queen, king, or ace, and any of the 4 suits, hearts, diamonds, spades, or clubs. So in other words, these are the outcomes in the event. 16 outcomes in the event divided by 52 total outcomes in the sample space, total cards in the deck. So 16 out of 52 is 30.8%. Note that we could also use a symmetry argument here. Sometimes this can be helpful in probability calculations. We note that as far as values are concerned, the deck really just contains 4 identical copies of the values 2 through 10, jack, queen, king, ace, if we're only concerned with values. So in other words, there's 4 2s, there's 4 10s, there's 4 kings, and so on. Well, I could just look at a single one of these, and I could treat it individually. I could say, what's the probability of getting a jack or higher? There are four ways to get that, four values: jack, queen, king, and ace, out of 13 possible values. And 4/13 is the same as 16 out of 52, right? Just divide a factor of 4 out of top and bottom. So we can use this symmetry, this fact that as far as just the values are concerned, there's essentially four copies of the deck, four copies of the values 2 through ace, that are in the entire deck. So sometimes that can be a helpful strategy in probability problems, taking advantage of something like a symmetry like that.